Well, we're up to the final section that we will cover for chapter 4. So we will be having a test real soon. Let's find out a few more theorems about triangles. Well, let's get started. Okay. Okay, isosceles, triangles, and equilateral triangles. A couple little theorems. These are pretty easy though. I don't think you'll find them too terribly difficult. So our objective, students will be able to use theorems about isosceles and equilateral triangles. Pretty simple enough. How are the sides and angles of a triangle related if two or more congruent sides or angles? Okay, so let's just go over some basics. Whenever you have an isosceles triangle, you have a couple things here. First of all, it's isosceles if you have two congruent sides. And what we will say is that if there's three congruent sides, it's automatically just equilateral. Okay, so we'll just, for my class, we'll assume that if it's isosceles, it's only two sides congruent. Okay, so anyhow, when we have an isosceles triangle, the two congruent sides are called legs, and the third side is not congruent to the other two. It's called the base. Now, the base you sometimes think about, oh well, that's because it's on the bottom, but that doesn't have to be the case. Isosceles triangles could be laying on their side, so you could have an isosceles triangle like this, where this side is congruent to this one, and then this one's the base. Okay, so please don't misunderstand. The base does not have to be laying on the bottom. It could even be upside down. Okay, we're having an isosceles triangle like this, where these two sides are congruent. Well, it's pretty ugly, but anyhow, you get the idea. The base side, the side that's called the base, doesn't have to be the base. Anyhow, you'll notice we also have what are called base angles, and let's talk about angles. So you'll notice this angle right here. It's made up of two rays, and every triangle has three sides. Okay, so basically this angle here touches two of the sides. Okay, the side that it does not touch, which is this one over here, is the opposite side. So we say that's the opposite side. That's the opposite side. Okay, opposite, and we'll abbreviate like that, opposite. Okay, and we'll use this in chapter 7, so you may as well learn it now. Opposite, you know, like in this case it's not like opposites like black and white or off and on and so on and so forth. It's just, we call it opposite. It's opposite over here. Now this angle here, okay, the opposite side is the one that it does not touch. You see this angle here, it touches this ray, or touches that side, and this angle also touches this side. But the side it does not touch is this one over here. So again, this is the opposite side. So now that we have that idea, let's go back and read this now. So we have the two angles adjacent to the base are called base angles. Alright, so anyhow, the base angles we're going to find out are congruent, and they're always opposite of the sides, or the two legs. And so we'll see that here in just a little bit. So here's the base angles theorem. So what we're saying is if you have an isosceles triangle, well then this angle here is congruent to this angle over here. And that is, the angles that are opposite of their sides are congruent. So this side, its angle that's opposite is here, and this side that's opposite is over here. And those two base angles are congruent. Well, I hope that makes sense. Okay, so it's a pretty easy enough theorem. We'll not have to spend too much time with that. But let's look at the converse. It turns out the converse starts out this way. It starts off, well, if you have the base angles congruent, then the sides opposite them are congruent. And so we'll go this way. And that's the converse. Remember, on the converse, you start out with a conditional statement where you have if P, then Q. Okay? That's this little arrow we use to mean then. Okay? The converse, remember, it switches the two around. So it says if Q, then P. And that's what happened. On the previous theorem, we started out with the with the sides were congruent, and then we said that these base angles are congruent. Okay, that was the previous theorem. Now everything just switches. Now we switch the P and the Q around. So now we start off with this first, and then we have the opposite sides are congruent. And so that's why we call it the converse. Well, that's pretty easy enough as well. So now a couple new theorems. Now let's look at a proof. Okay, so as most proofs, we should follow a couple ideas. We should start off with the given, all right, and we should work with the diagram a little bit. Okay, so we're given that JK in this diagram, JK is congruent to JL. So we have basically what we're going to do is prove the isosceles triangle theorem. So we start off with this. We have an isosceles triangle, right? That's what we start off with. Well, there's got to be some point in here that's the midpoint, right? So let's just say that's the midpoint. Well, then what we can do, we can then draw from this vertex, we can connect this segment to that midpoint. So this is the midpoint right here. You see what they're doing? Alright, well, since that's a midpoint, that means these are equidistant. So this side is congruent to this side. Well, by the reflexive property, this side is congruent to itself. So what we're going to say is that the top triangle is congruent to the bottom triangle by side, side, side. You see? And if those two triangles are congruent, then by corresponding parts of congruent triangles, that angle must be congruent to this angle. You see? So that's how this proof is going to work, and now we just need to write things out and more formally. So let's go back to our blue color. So MK, what we did is we drew those lines, definition of midpoint. We drew, the first couple reasons we don't use that often, so I've included them in there. But MK is congruent to ML. Well, MK is equal to ML. I wonder why we can say that. Well, it's because somewhere we said we had a midpoint, right? The midpoint means that this is right smack in the middle, right? So the reason that we can say this is related to that statement there. It's called definition of midpoint. Remember, often when you use a vocabulary word in a proof, there's the vocabulary word, midpoint, often it becomes the reason for another statement. So it's good to know your vocabulary words in geometry class. Come up all the time. Improves. Okay, so definition of midpoint. And I'm just going to abbreviate midpoint like that. Okay, midpoint. Definition of midpoint. Okay, so now JK is congruent to JL. Well, that turns out to be your given statement. That's kind of funny. Usually the given usually we start off with the given, and we could have started off with that, but on this particular proof they decided to do it as step 4. So this one's real easy. This one's given to us. It's part of our given. But if you take a look, what we have is we have the setup side, side, side here almost. Side, side, side. And we're going to get this side, like I said, congruent to itself by the reflexive property. So JM is congruent to JM. Hopefully you recognize that. We've seen it over and over and over again. That's simply the reflexive property. Okay, reflexive property. Alright, and so now we can say the two triangles right here are congruent by side, side, side. And if we look, the final step is to say that K is congruent to L. Well, now that's corresponding parts of congruent triangles are congruent. So there you have it. We just proved the isosceles triangle, base angles theorem, whatever it was. Okay? Alright, well, let's move on. So now let's do a practical problem. Use some numbers and so on and so forth. Let's back up, sorry. So, if the vertex angle of a triangle is 50 degrees, what is the measure of the base angles? Okay, so first of all, we need to identify that this is supposed to be an isosceles triangle. Okay, so isosceles triangle. Alright, so if the vertex of an isosceles triangle is 50 degrees, alright, so let's just draw an isosceles triangle. Doesn't matter really. An isosceles triangle, we do know that this side is congruent to this side. Now, the vertex angle, remember these angles down here are going to be called the base angles. So the vertex angle is up here. Okay, that's the vertex angle. Okay, and we know that that angle is 50 degrees. Okay, we also know that this angle here is going to be congruent to this one. We just proved it on our last slide there. So if we use that fact along with the other fact that all the angles in a triangle have to add up to be 180, and take 180 and subtract off the vertex angle, we basically have 130 degrees left. Well, those 130 degrees have to go here. So simply divide that by 2, get what, 65 degrees? So this angle here has to be 65 degrees, and this one has to be 65 degrees. And there you have it. We did a real simple problem. This angle is 50 degrees. Okay, that looks better. How about that? So that's a pretty simple problem. Alright, so these are a couple corollaries, and it's the first time I think we've seen the corollary word. This is kind of like theorem also. It means like it's a related law or related statement to the original statement. We had a theorem, okay, and it was called the base angles theorem. Okay, this was the original theorem. Now corollary is a related theorem to this one. That it's like a quick consequence of this theorem. So first, for example, we say that if a triangle is equilateral, then it's equiangular. Okay, so let me show you this in slow motion how it works. So we start off with an equilateral triangle, right? Alright, so I'm going to do this in different colors. So it's equilateral, right? So we start off with equilateral. So we have this side is congruent to this side is congruent to this side. So that's how we start. Now let's just consider for a second that we don't know this. Okay? Let's just say we don't know that side there. We could say based on these two sides here, okay, based on those two sides there, we could say that the base angles must be congruent. Well, so then that angle here is congruent to this angle over here, right? Well, now let's consider this isosceles triangle. This side over here, these two sides over here, the two blue sides. Well, we know that if this were an isosceles triangle and these two sides were congruent, then the base angles would be congruent. Well, that means this angle and this angle here must be congruent. And you'll notice this angle already has one tick mark. So if it's congruent to this one over here, it must also have a single tick mark. And now you'll notice all three angles here have a single tick mark. So it means then that this triangle is equiangular. All three of them are the same. So based on that, we can determine that each of these is going to be 60 degrees. How come? Well, obviously if three of the angles are all the same and they have to add up to be 180, okay, you just simply divide by 3 here and divide by 3 here, and x is equal to 60 degrees. Okay, so every equilateral triangle will be equiangular, and furthermore, the measure of that angle will be, of all three angles, will be 60 degrees. Alright, well, here's another corollary, and it's related to the converse one, and it works almost the same way. Let me just erase all this stuff. Alright. Okay, so on this one, you start off with an equiangular triangle, so that this angle here is congruent to this angle here, which is congruent to this angle here. And if you consider just those base angles being congruent, then the sides opposite have to be congruent, right? So that side is congruent to this side. Okay, so we're considering just this base angle and this base angle, okay? So if you consider just those base angles, then you'd have to say that those sides opposite. Well, suppose we consider these base angles over here, these two base angles, okay? The one that's up here and the one that's down here. Well, based on those two congruent angles, those are base angles, you can think of it that way, then the sides opposite must be congruent. Well, the side opposite of this one already has a single tick mark. The side opposite this one must also be congruent, so it must have a single tick mark. And so now you notice all three of the sides have a single tick mark. Well, that means they're all congruent. And so look at this fact. So either way we have it, if we start off with equilateral, then the triangle is going to be equiangular. And if we start off equiangular, then it's going to be equilateral. So these are both true. And so often what we have is the biconditional statement, where we have the if and only if statement. So we would say something like, a triangle is equilateral if and only if it's equiangular. So there you have it, pretty easy. So that's the idea behind a corollary. It's a theorem that's related to a previous theorem, and the previous theorem was this one. And the corollary here was related to the previous theorem here. And it's usually a real simple theorem. Follows real easily. Okay, so anyhow, let's use some ideas and see if we can figure out some stuff here. So find the values x and y. Well, notice in this triangle here we have the equal angular idea. And so then it's equilateral, which means this side here is congruent to this side is congruent to this side. And if that side is 4, then this side is 4, and this side is 4. Okay, so I already know quite easily that y is equal to 4. Alright, well, now what do we know? Well, we know that the base angles on this triangle over here, the base angles are congruent. Well, that means since the base angles are congruent, this side right here must be equal to this side over here. Well, I should probably draw it with one tick mark. Let me back that up. We should draw one tick mark here. So actually we only have one tick mark here, one tick mark here, because it's the same. Well, so in any event, that means this side is equal to that side. So that gives us an equation. 4 is equal to x plus 1. That's pretty easy. Move the 1 across, we get x is equal to 3. Okay, so that's using the idea of isosceles triangles, an equilateral triangle, and so on and so forth. Pretty easy problem, right? Well, here's one for you to try. Might be a little bit harder. Okay, so what do we have? We have an isosceles triangle, alright? So, since we have an isosceles triangle, the base angles must be congruent. So, that means this one's congruent to this one. And that means 3x must equal y plus 7. Now, hold up. We have two variables here, so you're probably saying, well, how do I solve that now? Well, we can also use the idea that, hey, this angle up here is 90 degrees, right? And if the base angles are congruent, and if all the angles have to add up to be 180, so let's take a look here. We take 180, we subtract off 90 for this angle right here, and what's left for these bottom angles? We have 90 degrees left. Well, if those are congruent, then these must both be 45 degrees. You see? Oh, so then that means we can deal with an easier equation than that. We can say, well, hey, 3x is simply equal to 45 degrees. And so we divide by 3, and we get x is equal to 15. Okay? Alright? Well, the same is true on this side. Y plus 7 must also equal 45 degrees. Alright, when we subtract 7 here, subtract 7 here, we'll get y is equal to 38. Alright, so there you have it. So that one's a little bit trickier. You have to watch out, figure out what you're given. This was a key piece of information right there. Okay, we needed to know that. That allowed us to find out that those are actually 45 apiece. And so a little bit harder problem. Well, so we've seen quite a bit. Angles opposite, equilateral, congruent. If two sides of a triangle are congruent, then the angles opposite them are congruent. The converse is also true. So there's a little bit of a summary and we're done. So let's